Hello everyone and welcome to another math tutorial. This is the second video in our linear unit, and in this video we're going to talk about linear inequalities. Not just how to solve inequalities, but also how to express their solutions. Alright, before we jump into some problems to solve, I want to go over the different types of notation that we can use to illustrate our solution to these inequalities. The first notation that you're going to probably be familiar with already is simply called inequality notation. Inequality notation is simply the place where you're going to get to when you're solving an inequality. We can also express our solutions on a number line, and then finally we can express our solutions in what we call interval notation. This is the notation that's probably going to be in large part new to you, possibly if you're watching this video, so I'm going to kind of go over this from an introductory standpoint, and then every problem that we do, we're going to put our solutions in this interval notation. Okay, the first one, the inequality notation says x is less than 3. First thing I'm going to do, I'm just going to go ahead and put some numbers on my number line. Some people will put 0 in the middle. You can do that or not do that. That's totally up to you. I need to get to 3, so I'm going to kind of put maybe 3 somewhere near the middle, so maybe 3 can live right there. And then I'm just going to build around that number. If we want to show all the values on the number line that are less than or smaller than 3, I need to show all the numbers over here. And what I'm going to do is use an open circle on 3. Open circle means we're not going to include the 3. And then I'm going to shade my number line to illustrate where the numbers are less than 3. And I'm going to end with an arrow at the end of the number line. Now the interval notation is going to be a little different. The interval notation is written kind of like an ordered pair coordinate point, which is going to illustrate between what two numbers on the number line we are shading. Now we do have a number on the right boundary where our shading stops, which is at 3. But we don't see a number on the right or on the left boundary where our number line stops being shaded. So you have to remember that the number line continues out towards positive infinity on the right and towards negative infinity on the left. And so we're actually shading this number line between negative infinity and 3. So my interval notation is going to be negative infinity comma 3. And now I'm going to use either parentheses or brackets based on whether I'm including or not including the numbers. So positive 3 is not being included. And when you're not including, you're going to use a parenthesis. Infinity and negative infinity, by nature, you can't ever equal infinity or negative infinity. So that's also a non-included value. So we're also going to use a rounded parenthesis on that end. Okay, next one, we've got x is greater than or equal to negative 2. I think I'm going to position my 0 right here. Okay, so greater than or equal to negative 2. So the difference between this one and the last problem is I'm going to fill in the circle where negative 2 is. The filling in is for the equal to on the negative, or on the inequality. I want to include that number. And then greater than negative 2 goes out to the right. And now I need to write in intervals. My interval this time, and I'm reading, I didn't say this in the last one, but I'm always reading from left to right. And so from left to right, we start at negative 2, and then we shade on out towards the positive infinity direction. Now here, negative 2 is included. It's a closed circle. So in contrast to the last problem where we used a parenthesis, we are going to use a square bracket. And that bracket indicates closed circle, indicates equal to. And on the infinity, we're going to use a parenthesis. Again, because we're not going to be able to equal infinity. Okay, the next two are compound inequalities. Compound inequalities, in this one we are wanting to show all the values on the number line that are between negative 3 and 2. So all the numbers that are greater than negative 3 and all the numbers that are less than or equal to 2. So in essence, between those two numbers. So let's set up the number line. I'm going to put negative 3 out here. We'll just go all the way on the end with it. Negative 3, there's no equal to on that inequality, so that's going to get open circle. And then the 2, there is an equal to, so we're going to close that. And then I want all the numbers that are bigger than negative 3 and less than 2, which is all the numbers between those two values on the number line. My interval now, read from left to right, start at negative 3, and I stop at 2. The negative 3 is not included. The positive 2 is included. Okay, and the last one, we have another compound inequality. This is an OR statement. Solutions can be less than or equal to -1, or they can be greater than 3. So we're going to show both those on this number line. Go ahead and drop maybe -2 there. So less than or equal to -1, I'm going to want a closed circle at -1, and less than would shade to the left. And then greater than 3 is an open circle, and it shades to the right. So this particular number line is actually different than the other 3. It's showing 2 different areas or solution regions. And I'm going to write an interval for both of these regions. The first region, as I read from left to right, starts at -infinity and goes to -1. Parenthesis on the infinity, bracket on the -1. The second solution region goes from 3 to positive infinity. We're going to use a parenthesis on the 3 because it's not included, a parenthesis on the infinity. And between these two, we're going to connect them with what looks like a capital U. And what that U stands for is the union of these solution sets. We use that U when we have OR statements on our inequality. Basically just saying again that the solutions are in this interval or this interval here, which is what the number line shows as well. All right, let's jump into some problems. When we solve our problems, again, the solutions are going to look like this. We're going to graph them on a number line, and then we're going to write our solutions in this interval notation. Okay, here we go. First problem. 17 plus 3x is greater than 29. I'm going to begin by subtracting the 17. So that's going to give me 3x is greater than 12. And divide by 3, we get x is greater than 4. Let's illustrate x is greater than 4 on a number line. So you're going to be able to draw your own number lines. I don't care how you space out the number line. Personally, as a teacher myself, it doesn't matter to me. I don't necessarily need to see 0 right in the middle either, because that may not make sense based on the size of this number. So you set it up how you want to set it up. I'm going to put that number somewhat near the middle. I'm just going to build around that number. 0 might end up on the number line, it might not, and that's okay with me. So x is greater than 4. I'm going to start at 4. Greater than is going to be numbers bigger than 4. So we have to go out to the right. And then my solution, my interval notation would be everything from 4 to infinity. All right, the next example is going to begin with the distributive property of the 2 inside that set of parentheses. So that's going to give me 3x plus 10 minus 4x is greater than or equal to 15. Combine the like terms, which are the x's here, 3x and -4x, are going to be -1x plus 10 is greater than or equal to 15. I'm going to combine my constants by moving the 10 over to the right hand side. So that's going to be -1x is greater than or equal to 5. And to complete this, we have to divide by -1. Now you've probably seen this rule before viewing this video, but anytime you multiply or divide by a negative number, the inequality is going to change directions. So we should end up now with x is less than or equal to -5. Let's number line that solution. Put -5 kind of near the middle. I like to put a couple of numbers around that. It's typically how I make my number lines. Less than or equal to -5 needs to be a solid point at -5, and then less than goes to the left. My solution then is going to be everything from -infinity to -5. And again, I'm using a bracket on the -5 because it's a solid point, because it's an equal to. Bracket means equal to. Okay, next example. I see I've got one term that's got a fraction in it. I don't want to deal with that fraction, so I am going to begin my problem by multiplying everything by 3. And so if I do that, I get 12x plus 42 is less than or equal to, so now when the 3 distributes to the fraction, it will cancel the 3. And so I'm going to have 2x plus, and then 3 times 7 is 21. Numbers are a little bit bigger. That's okay. For me, that's easier having numbers slightly larger than having to mess with the fraction. So that's how I choose to do this problem. I'm going to take my 2x over to the left-hand side by subtracting it. I'll take my 42 to the right by subtracting it. So those terms are going to cancel out. I now have 10x is less than or equal to negative 21. If I divide by 10, I get x is less than or equal to negative 21 tenths. Or if you prefer, x is less than or equal to negative 2.1. Okay, let's take that to a number line. You can use the decimal or the fraction, it doesn't matter. I find it easier to, if I'm gonna put my solution point, that negative 2.1 kind of near the middle of my number line, I find it easier to build around that if I use decimals sometimes than fractions. How you build around that's totally up to you. I'm gonna call this negative 2, this negative 1.9, so I am just going by tenths, like so. But again, however you want to do it's totally up to you. I want a solid closed circle at 2.1 because the equal to, and all the numbers less than that are going to go out to the left. Okay, my solution then as an interval is negative infinity to negative 2.1, the bracket, or you could write negative infinity to negative 21 tenths. Either of those are going to be fine. Just depends on how you want to write that number. Okay, the next few examples we're going to look at are what we call compound inequalities. And a compound inequalities are two inequalities that are connected by either an or statement. We'll do a couple examples of the and. I'm going to do one of the or. And an and problem, what you're looking at is you're looking at the intersection of two solution sets. If I can highlight something here, that would be it. You're looking at the intersection of two solution sets. Think of intersection as like overlap. A number is a solution if it solves both inequalities. When we see an or statement, it's not an intersection, but it's the union of the two solution sets. And a number solves, or is a solution, if it solves at least one of the two inequalities. Doesn't have to solve both, it solves one or the other. So let's go ahead and take a look at some examples of compound inequalities. Okay, I want to do two examples of the and statement compound inequality because the and statement can be presented a couple different ways. So I want you to kind of see it both ways. First way, like this, is it can just be two completely separate inequalities. And what you're going to do is just solve each one of these separately, and then you're going to put the answers together. If I was solving these, I'm going to be dividing by 3 here to get x is less than 2. I'm going to subtract 4 to get x is greater than or equal to negative 4. Okay, so there's my two solutions. This on a number line. Again, build it how you want. I'm going to do maybe 2, 4, just count by 2s here. That seems to work okay. So here we go. I want to show all the values, all the solutions that are less than 2. So less than 2 would start there and it would shade. Some people like to do this. Let me show this. I'm going to shade this direction. Greater than or equal to negative 4. So negative 4 is here. There's an equal to, so it's solid. Greater than is going to shade this direction. And you can see how those two shadings are going to overlap each other, right? They're going towards each other. So my solution, since intersection, a compound inequality with an and statement, has to solve both of them, I'm going to shade just between those two numbers, and that's all. My interval notation then would start at negative 4 and stop at positive 2, using bracket on the negative 4, parenthesis on the 2, because of the equal to or not equal to on those inequalities. Okay, the second example I want to do of the and statement inequality is probably the more frequently seen setup for this type of problem. And it's where you have the two inequalities kind of conjoined. They're put together. They share the same, in this case, 3x plus 9, right? This inequality could be split as 2. I could write, let's just go ahead and do that, even though I'm not going to solve it this way. But I could write 3x plus 9 is less than 18. And if I cover up the 18, I could write 3x plus 9 is greater than or equal to -6. So there's two inequalities there. They both share 3x plus 9. So to solve them, I'm going to be doing the same exact steps. And so the idea is let's just do those steps one time and we'll solve kind of both of them simultaneously. So if I was solving this, what I would do is I would begin by subtracting the 9 to that side. Well, if I was solving this one, I would do the same thing. I would subtract the 9. So I'm just going to do that to both inequalities. Take that positive 9 out of the middle by subtracting it to both ends. So if we do that, we get -15 less than or equal to 3x is less than 9. And then to finish solving this, I have to divide the 3 off the x. I'm going to divide to this inequality, and I'm also solving this inequality here. So I'm dividing 3 to both of those ends, and I end up with -5 is less than or equal to x, which is less than 3. So that's solved. I like this a lot, actually. It also kind of preserves the idea that with this intersection that the solution is going to be between two numbers. And so I like this because x is physically written between these two numbers, so it interprets easy on a number line for me. It's a lot of space between those two. I'm going to do something like this, maybe 1, 3, 5. Just going to count by 2s, but odd numbers, so I can get the 3 and the -5. So I want open at 3, I want closed at -5, I want everything in between. So there's my number line. My interval notation is then bracket -5 to 3, parenthesis on the 3. Okay, the last example in this video is another compound inequality. We're going to look at the OR statement, which is the union of the solution set of this inequality and this inequality. Now typically your OR statements are going to be separated like this. So I'm not going to show you two examples of this. We're just going to work the one example problem. So I'm just going to begin by solving each of these. So let's see, I'm going to start by subtracting 1. So we get 2x is greater than 8. And then divide by 2, x is greater than 4. Or, and up here, if I subtract 4, it's just a single step. So I'm going to write my answer down here. If I subtract 4, we get x is less than -3. All right, so our solutions are numbers bigger than 4, smaller than -3. Let's show that on the number line. I'm going to do this one real simple. I'm okay as a teacher if you do something like this. There's 0, maybe 4 lives out here, -3 lives there. If you want to fill in all the numbers in between, by all means, you can certainly do that. I want numbers bigger than 4, which is that way. I want numbers less than -3, which is that way. Going from number line to the interval solution, I want everything from -infinity to -3, or everything from 4 to +infinity. Okay, that concludes this video. If you found the video helpful, please give it a thumbs up. If you have any questions, there's two things you could do. One, you could leave a comment down below and I will try my best to answer that. The second thing you could do if you have some questions or if you want to see some more examples is you can go to my extra practice video where I'm going to solve maybe 3 or 4 new example problems just to give you a few more opportunities to see these types of problems worked out. Okay, I thank you for joining me for this video, and I'll see you in the next one.